go ahead to continue to talk about the matrix. What are matrix? We talked about operator already. The operator is to rotate, right, the vector in the hyperspace. We talked about that already. And they're represented as the matrix, right? Like the CNOT gate, Hadamard gate. Good. But there's a special matrix called the Hermitian matrix. First, let me introduce that there's something called adjoint matrix. So what is this? So if A is a matrix, then A dagger, which is equal to A transpose followed by complex conjugate, is the adjoint matrix of A. Okay, so for any matrix, you take the transpose and then you take the complex conjugate. Then that is the adjoint matrix of A. For example, if I have matrix that is I1, 0, I, okay, its adjoint matrix, it is the dagger. So it is equals to I1, 0, I transpose dagger, complex conjugate. What is transpose? You will just draw a diagonal line and then flip over the element. So all those on the diagonal are still there. But then I'm going to swap this ij. This is element first row, second column. It becomes second row, first column. Second row, first column becomes first row. Second row, first column becomes first row, second column. So I'm doing this reflection, right? Do you see this? It's the same for other higher dimension. But besides this transpose, we will going to take the complex conjugate also. Okay, so we say this is the adjoint matrix of the original matrix. Okay, this matrix is the adjoint matrix of this matrix. Just some definition. Okay, nothing special at this moment. But then now we're going to introduce, for some matrix, its adjoint matrix equals to itself. Then we call A is the self-adjoint or the Hermitian matrix. This is a very important matrix in quantum mechanics. Okay, so what we have just said, basically just say self-adjoint. What we basically just say that we just gave a definition of adjoint, and then if it equals to itself, then it is a Hermitian or self-adjoint matrix, and so we have A dagger equal to A. Okay, for example, I have something called sigma y we're going to study later, which is 0, negative I, 0. What is the adjoint of sigma y? Well, first I will do a transpose and then followed by the complex conjugate. When I do transpose, I just swap the about the diagonal, right? So I have moved this one to here and this one to here. So I just swap them. And then apply the complex conjugate, then it will get negative again. This one become I, which is just equal to sigma y. Yeah? So this is a Hermitian matrix. Okay? Then what's so special about the Hermitian matrix? The Hermitian matrix has the eigenvalue real. Okay, I'm not going to prove it, right? You can read my book, right? Otherwise, just take it for granted. Their eigenvalues are real, right? So what is eigenvalue? Eigenvalue of a matrix is that you can find a vector V. So the matrix times the vector equals to a value times the vector. Just a pure number. This is a number. Okay, right? And this is a vector, right? And this is a matrix, right? For example, you will be able to find sigma y, right, times a certain vector. I kind of forgot. I think it can be let me don't use sigma. I forgot the eigenvector of sigma y. Let's say sigma z, right? I'm not going to talk about sigma z yet, but I did not give you. Or z, I actually gave you z, right? I can tell you z times a certain vector equals to minus 1 times that vector, right? And z is what we talked about earlier, the z gate. It times 0, 1 equals to negative 0, 1. You can see that, right? And this is like negative 1 times 0, 1. So the eigenvector here is 0, 1, and the eigenvalue here is negative 1. Is that okay? Yeah. Okay. It's just saying that I have this matrix times a vector. It's just equal to a number times that vector. So basically in the space, you can see that it does not rotate the vector. When you apply a matrix to a vector, you expect it to rotate. But for an eigenvector, when you apply the matrix to its eigenvector, it only scales the vector instead of rotating the vector. Okay. But here I want to say that this, if the Hermitian, it is a Hermitian matrix, that matrix must have a real eigenvector. And why this is so important? Why? That is because of this Bond's rule, right? So it is said that if an observable, when we do measurement, those are observable, we get something, right? They always correspond to a Hermitian matrix, right? So we will gradually understand what it means. But for example, when you measure the spin, it corresponds to the Pauli matrix, right? For example, the spin it might be correspond to a Pauli matrix sigma z, right? Which we just discussed, right? When we measure it with some normalized function, right, in the state, the result will be one of the eigenvector. They basically say that when I measure the spin and the corresponding matrix must be Hermitian, because the eigenvalue we measure must be plus minus 1, right? You measure the spin is either going up or going down. Okay? And then the probability of measuring the a certain value, of measuring a certain value is equal to the projection operator corresponding to that lambda. Now, so this is a little bit troublesome, right? You don't know what I'm talking about, right? I'm going to explain it. But the point is that I want you to now, right? We are rather fast because we discussed in other class, but you can take it for granted. The point is you agree that every operator, every matrix, they rotate the vector, right? That's what quantum computing about. You rotate the vector in the hyperspace. There is a special vector, a special operator. They are Hermitian, means this one, right? They are Hermitian. Because they have real eigenvalue. And why? Because all the Hermitian operator, right, will correspond to some observable, or maybe I should say all of the observable will correspond to some Hermitian operator. For example, you measure the velocity, measure the position, or measure the spin up and down. You have a corresponding Hermitian operator. What you measure are actually the eigenvalues of this Hermitian operator. Right? So, for example, here I told you that Z has an eigenvalue of -1 or +1. I did not show here because it has two eigenvalues. Right? So when you measure the spin, you can be either plus or -1. And this plus -1 turned out to be the eigenvalue of Z. And because it's the eigenvalue of Z, and because it is measurable, it's observable, it's our real life, it must be a real number. It cannot be a complex number. Okay? So these are the relations between Hermitian matrix, observable, eigenvalue, and the real value of the eigenvalue, right? So I hope you can associate this, right? Now, but what is the probability of measuring the eigenvalue? We actually know already, right? We actually know that already. Remember that if I say I have a state which is psi equals to alpha 0 plus beta 1, we say the probability of measuring 0 equals to alpha star, or the magnitude of the alpha square, right? The probability of measuring 1 equals to beta star, which is the beta square. But this is not convenient. This is a simple case. We can see the coefficient, but we're doing derivation or whatever. You cannot do that, right? So the one way to do this is to use the so-called projection operator, right? So let's be patient. Let